Okay, so this is objective 7.2D with the topic factoring and simplifying trig expressions. And it's a little bit of a detour from what we were doing yesterday. But in order to do the things that I would like to do on Friday, which includes what we did yesterday, it also includes what we're doing today. So we're going to learn these things in isolation and then we'll put them together. So you will be successful when you can identify when you need to factor, and then you can simplify like trig expressions. So you know I'm going to put a little dash between them, like trig expressions, like terms. Okay, so here are some things that I would like you to know and remember. You factor trig like you factor polynomials. Factoring just really never goes away in math. So some basic things to remember. The difference of squares. Is a simple formula where we say, okay, perfect square, a squared minus b squared factors down to their conjugates of their square roots. So that would be a minus b times a plus b. Conjugates means that the signs change. 1 plus 1 minus. Square root of a squared is a. Square root of b squared is b. 1 plus 1 minus. So that's a difference of squares. That one should be something you can access pretty quickly. We do that. We factor that format often. One that we don't factor often is the sum or difference of cubes. And I am not going to write two formulas. I'm only going to write one, but I'm going to write a formula with double signs in it. So I'm going to color code my signs. So first of all, sum or difference of cubes. So we have a cubed and b cubed. And what I'm going to do is I'm going to color code my signs. If it's the sum of cubes, I'm going to use a red pen. And I'm going to put my signs in the top. If it's the difference of cubes, I'm going to use my blue pen, and I'll put the signs on the bottom. So when you're doing your sum or difference of cubes, follow the color. Okay? So this is how this factors. It factors into a binomial times a trinomial all the time. It's a pattern that you have to memorize, and I don't think that we often encounter it, so it's easy to forget. So I'm going to pick up my red pen first, and I'm going to tell you how I do sum or difference of cubes. I'm going to do sum first. So I've got my red pen. I always just recite to myself what are the signs in these binomial trinomials. It goes like this. In the binomial, I'm going to keep the sign the same. Then my next sign in my trinomial, change the sign to minus. And then my last sign in my trinomial, add. Keep, change, add. And that's all about the signs. Now I'm going to go with my blue pen. Again, remember what I said. I always do my signs first, and then I go back and I plug in my numbers or my variables. So keep, remember? So now we're doing the differences cubes. Keep it, change it, add. Keep, change, add. So maybe write yourself a little note. Keep, change, add. That's for the signs. Now I'm going back to my pencil, and I'm going to fill in these 5 spaces. So in this space, I'm going to take the cubed root of a cubed, which is a, and in this space, the cubed root of b cubed, which is b. Okay. Then, in this next position, the rest of a cubed, which is a squared. And then I switch all the way to the back, the end, and I put the rest of b cubed. So that would be b squared. So I have a times a squared is a cubed, and b times b squared is b cubed. Now I'm just concerned with what goes here in the middle. Does anybody know? It's not 1. It's A, B. You just put these two terms, whatever they are, you just multiply them together. Don't worry about the sign because you've already put them in. Okay, so if you're adding cubes, do the red signs. If you're subtracting cubes, do the blue sign. Okay, so there's that. A couple other things I would like to alert you to or have you be thoughtful about. So I'm going to do this. Remember. And I'm going to make it an electric reminder. Like I'm going to zing you if you forget to do it. Zap you, zing you. I like zing better than zap, but there you go. Remember, the product of reciprocals is 1 all the time. For example, A over B times B over A equals 1. True statement? So, how does that apply, do you think, to the trigonometric functions we're working with now? Reciprocals. Does anybody think they can write a statement where you're multiplying two trig functions that equal 1? Okay, I'll start. Sine of theta times, what's its reciprocal function? Cosecant of theta equals 1. Are they not reciprocal functions? They are. Now, I could prove it quickly by decomposing cosecant into sine, so I'll do it up here. So sine of theta times cosecant of theta, which is 1 over sine of theta. Look at that. Cross simplify. Boom. 1. So that stands to reason that what are the other two that I should know? Cosine of theta times secant of theta equals 1. And tangent of theta times cotangent of theta equals 1. So be on alert if you see any of those statements. Okay? Because they're reciprocal, so they multiply to 1. And then as we go along, I'll add more little zingers for you to remember. Won't kill you with too many zingers in one day. All right, so let's practice some factoring. So here are 4 different trigonometric expressions that contain powers. So anytime I see powers, I wonder if I can factor. Walking away from my computer. Pause. I'm going to close the door. So I look at the first one, problem A, and it says sine squared theta minus cosine squared theta, and I'm asking you to identify that format. What do you see? Somebody sees the difference of squares. Look at it. Is he right? Perfect square minus perfect square, right? Now, maybe you want to go back and rely on, remember when we used to substitute when we had crazy looking things we had to factor? We'd simplify it by letting, like, y to the 4th equal x squared, and remember we used to do that? So, for example, you could just say, all right, so sine is going to be x, so x squared minus y squared, or a squared minus b squared. If that will help you to see it and factor it, then do that. So we can let sine equal x and cosine equal y all the time when we're trying to factor. So it's the difference of squares, right? So you're just breaking it down into their conjugates. So what would this look like? Imagine 1 minus 1 plus. Square root of sine squared is what? Sine of theta, sine of theta. Okay. Square root of cosine of theta, so cosine squared? Cosine theta, cosine theta. And if you had to factor it first in X and Y to see it, that's okay. Use whatever strategy works for you. But train your mind to understand that they are pretty much the same thing. They're just different forms of an unknown value. X is unknown. Sine of theta, I don't know what that is. I have to have more information to know that. Questions? So that's the difference of squares. Let's look at the next one. I see a trinomial. 3 terms. So when I'm factoring 3 terms, I usually go to an alternate method for factoring. So here's the first thing. Anytime I'm given a trinomial, I always make sure that my exponents are either in descending or ascending order. So this is exponent 2. This is exponent 1. This is exponent none, right? 2, 1, none. Descending order. Okay, so maybe I don't like it in secant alpha. Secant alpha is throwing me off. So I decide to make secant alpha f squared plus f minus 12. Maybe I want to change it. You can pick any variable you want. You could make an apple squared plus an apple minus 12. I don't care. But what's our strategy? So we're looking for numbers that satisfy the conditions. Multiply to negative 12, add to 1. That's what we want to know. So what are those values? 4 and negative 3. All right. So I could say, all right, so that's 4f plus 4, f minus 3. If I want to factor it as an old-fashioned trinomial, and then just go back in and replace f with what? Secant of alpha plus 4 times secant of alpha minus 3, factored. So see, you guys already have the skills you need to do this. You just have to train yourself to see that it's really the same thing. It's just trig language instead of algebra. Okay? Look at the next one. What do you see? Sum of cubes, right? So again, you could go ahead and convert this to a cubed plus b cubed if that will help you to factor it. But I'm wondering if we can get away from that. Remember the signs in our binomial? Let's do the signs first. It's sum. So what do we put in our binomial? Keep, change, add. You with me? Okay, so we're doing the sum of cubes. All right. So how many cotangents of beta do we want in this first position? 1. All right. So cotangent of beta. And how many tangents of beta? Tangent of beta to the first power. Okay, so those are the first powers. All right, what goes here? Cotangent squared beta. Yeah, because we want the squared. And then let's do the last position. What goes here? Tangent squared beta. All right, now all we have left to do is the middle. Remember what the middle is? Put them together. So that would be cotangent beta, tangent beta. I'll give you a second to think about that. Zing. 1. You're multiplying reciprocals. Oh, yeah, look at that. Simple. Simple, simple, simple. Okay. Other things I could tell you to look for is cotangent of beta, cotangent squared beta reminds me that maybe it's a Pythagorean identity, but cotangent squared beta and tangent squared beta aren't part of the same Pythagorean identity, so I can't simplify it anymore, but there you go. Here we go on to the next one. Here we have another binomial. By the way, that's not a y. What is that sign? Gamma. Yeah, I wrote it up on the board. See? Okay, so it's gamma. All right, so you have a binomial, and it's subtraction. But is it the difference of squares? It is not. 3 is not a square. 6 is not a square. Tangent of gamma is not a square. What am I going to do? Maybe if I change tangent of gamma to be x, right? 3x squared minus 6x. Does that help you see it? Do they have something I can factor out greatest common factor? Yeah, if I take a 3x out, that leaves me with x minus 2, right? So sometimes it's just greatest common factor. And I think we forget to check that because that's something that we did so long ago. We're always more focused on the ones that are more difficult to factor. So let's write it in the right format here. So that would be 3 tangent gamma times tangent gamma minus 2. Factored. Really important skill to develop when you're working with trigonometric expressions. Okay, so you have to, this is why we take algebra before we take trig. Imagine trying to learn to factor at the same time. That would not be fun. Okay, let's move on. Now, I think we can finish this. Okay, so let's do it. Simplify the expression into its most simplified form. I tried to write that in other ways so that it didn't have simplify and simplified. Just couldn't do it. I needed a thesaurus. I love to say it the wrong way. P.S. There's a typo in A. In the denominator, sine squared is not a complete thought. It's sine squared alpha. So squeeze that little alpha in there. Okay, so I'm asking you to simplify fractions. This is kind of like me saying, okay, I have 5 over 10. What would I do? Reduce that to 1 over 2, because that would be 5 times 1 over 5 times 2, so I could cancel out the 5s, and that's what I'm doing. This is all I'm doing with all of these fractions, is I'm writing them in their simplified form. Now, the way I handle each one is well, these two I handle pretty much the same. This third one is a totally different bag of marbles. And man, it's an annoying bag of marbles, but that's okay. We have to do it. Let's start here with problem A. You have sine of alpha minus cosine alpha over sine squared alpha minus cosine squared alpha. And I'm asking you to simplify that. So typically when I see powers in fractions, I try to factor those powers down to the power of 1. So that I can find all my common factors. So my numerators are power 1, sine to the first power, cosine to the first power. So what do you recognize in the denominator? Difference of squares. Do you see it? We've already factored that today. So I'm going to rewrite the numerator, sine of alpha minus cosine of alpha over, and I'm going to switch colors to show that this is something that I'm changing. I'm going to rewrite the denominator in its factored form, which is sine of alpha minus cosine of alpha times sine of alpha plus cosine of alpha. That alpha is terrible. Oh, I don't like that. I'm going to fix that. Okay, so remember what I told you in your instructions. You need to learn to find like expressions. Can I simplify this fraction? Do they have like terms? What in the numerator is like the denominator? The binomials, right? Completely match. So I can say that's 1 over sine of alpha plus cosine of alpha, because I can cancel common binomials or common expressions. They're like expressions. Okay, they have to match exactly. They have to match exactly. So look, your answer is much simpler looking than the original fraction. And you are always going to be required to simplify your fractions. Okay, so let's look at the second one. Second one is all in secant and numbers, secants and integers. So I got a power in the numerator and two different powers in the denominator. What do you think we should do? What do you recognize in the numerator? Perfect square? How about 9? It's the difference of squares again, right? 9's a square. So let's factor that. I'm going to grab my red pen to show that I'm changing something here. All right, so that would factor down to what? 1 minus 1 plus, right? And 3 and 3, definitely we know that. You're just taking the square roots of both. So it's the square root of secant squared beta. Secant beta and secant beta plus 3. Again, you have the autonomy to go over here and decide, I'm just going to do x squared minus 9 and factor that first and then reinsert secant beta for x. That's okay. Let's look at our denominator. Trinomial, right? So maybe we still just don't see how to factor these trinomials without writing it in an alternate form. So maybe we would write it as x squared minus 5x plus 6. Maybe at least we do that for now, just so that we can find the two numbers that we're looking for. You don't have to. So I'm looking for numbers that multiply to 6 and add to negative 5. What two numbers satisfy those conditions? Be careful. Negative 3 and negative 2. Because they multiply, negative times negative is positive 6, negative plus negative is negative. 6 and 1 and 3 and 2. You have to be careful. Watch your signs. Okay, so here's what I know. I'm going to do a negative 3 and a negative 2. That's what I needed. I needed the numbers that multiply to 6 and add to negative 5. That's all I needed. So now I just have to do, so remember we were going to do x minus 3, x minus 2. What am I going to replace x with? Secant of beta. And secant of beta. Okay. Now all we have to do, I'm going to grab my black pen here, is simplify, yes? So I would cross out my like expressions, and I would be left with the answer secant of beta plus 3 over secant of beta minus 2. And those are not like expressions. And I cannot simplify part of them because I don't know what secant of beta is. It's an unknown quantity. So I can't just go, oh, okay, well, that's negative 1.5. No, it's not. Because you don't know what secant of beta is. So be really careful not to make errors like that. I don't think it's going to let me back up without erasing a lot of things. Oh, it did. Okay. Last problem. Oh, we got 10 minutes. We can get this done. First of all, I'm going to tell you what the answer to this problem is. And you're going to go, what? The most simplified answer to number C is cosine theta. So that crazy looking fraction right there reduces down to cosine theta. So let's see how we go about making that happen. We have to go with a different, oh, sorry, Emma, I haven't loaded it yet. We have to go with a different method than we've tried before. Because all of these trig functions or trig expressions are they're all to the first power, but they're also all different functions. So I'm going to decompose them into sine and cosine because that's what they all have in common. Because then maybe I can do some math with them. So I'm going to rewrite. And every time I change something, I'll go to my red pen. So we're going to do 3 minus, and we're decomposing cotangent into terms of sine and cosine. So I'm going to grab up my red pen, replace cotangent of theta with sine cosine notation. What is it? cosine of theta over sine of theta. Okay? Remember, the sooner you memorize that little piece of information, the better off you'll be. I'm going to pick up my black pen again for this 3, but I'm going to replace secant with its reciprocal function, 1 over cosine of theta. Okay, I'm pick up my black pen one more time. And then I'm going to my red pen. So, cosecant of theta in terms of sine or cosine. 1 over sine of theta. Okay, so really complex fraction here, but at least all of the functions are now speaking the same language. So we have multiple methods that we could go about to solve this equation. Now, or to simplify this complex fraction. Now, I have taught you to write complex fractions so that all the denominators are the same, right? And then we just cancel out the denominators and we're left with the answer. So we're going to continue with that strategy. Now, to do that, they all have to have the same denominators. So when I rewrite it here, I'm going to pick up my black pen again. I'm going to go ahead and write this 3 over 1. And I'm going to leave a space because I'm going to change it. So I'm going to leave a little space. Minus cosine theta over sine of theta. Okay. And then I'm going to do the same thing for the denominator. I'm going to leave some spaces. First, I'm going to multiply these two things. So would you agree that that's 3 over cosine theta? Okay, and I'm going to leave a space to do some changing. Minus 1 over sine of theta. Okay, so now we're going to make some changes. So I'm going to pick up my red pen, and I'm going to think about the jealous denominators. Denominators are jealous. They want what the other denominators have. So this one wants what? Sine and cosine. So I'm going to get, okay, so that's going to be times sine theta cosine theta over sine theta cosine theta. Sorry about my messy. Okay, so now that first number has sine theta cosine theta in the denominator. And do you think these other ones want ones or they already have them? They already have them. So what does this denominator want that it doesn't have? Cosine theta over cosine theta. We're just writing like fractions here with like denominators. On the denominator, here, what does this cosine of theta want? Sine of theta over sine of theta. All right, and then this one here. It wants cosine of theta over cosine of theta. Okay, so here's what I'm really happy to announce. Now we are going to get rid of the denominators. Just like this, they're all the same. I don't need them anymore. All right, so I'm going to write down here because I'm out of space up there. Are you ready? So in my numerator, I have 3 sine theta cosine theta minus cosine squared theta, because it's cosine theta times cosine theta. You okay with that term? That notation? All over 3 sine theta minus cosine theta. Wait, man, they're so close. And I told you the answer was cosine theta. What do you think? Look what's in my numerator. A square. I don't want that. So, and what do these two terms have in common? So let's factor it out. So I'm going to grab up my red pen to do that. Cosine of theta times, what's left? 3 sine theta minus cosine theta all over 3 sine theta minus cosine theta. And guess what? Cancel, cancel. What? Can you believe it? Cosine theta. Ta-da! P.S. This skill, super important to develop. Taking complex fractions and simplifying them quickly. Use the jealous denominator. That's such a great strategy. Okay, so your homework's on Canvas, except it's not. I'm going to load it right now. And I said 7.2D, and you have to do the odds. So that's 10 problems. But I've also said I encourage you to do the evens for extra credit, because I believe the more practice you do, the better off you will be. Also, tomorrow, I am going to provide time in class to do some more practice before we go into verifying trig identities. And so, evens extra credit. I wouldn't spend too much time tonight doing the evens, but definitely do the odds, so that tomorrow when we grade, you know if you're on the right track or not. Okay, thank you.